Dear students, welcome to another lecture on machine design. Continuing with yesterday's lecture, you see here in YouTube, I have found out one quarter joint animations. You see, some of you may be finding it very difficult to understand how this whole thing is. You see, I will show you this how it works. You see, these are the tensile pulls, and what is this? This is the socket, and this is the rod. You see, when you are pulling it now, it may tear off like this because of the tension. So what is the resisting area? This is the resisting area. This is what we should break. So that is, you have to draw the diagram there, and you have to say pi by 4 d square. That is the failure. Now this quarter, if we are pulling it like this, you see quarter may fail like that. You see this so this is the area. You see, I want to tell you here, you see, though here it is curved like this, okay, but still no, we take it as rectangular only. So the area will be this breadth b into t, and it is failing not one place, two places. Therefore it is two times. Okay, that is the that was the failure of the cutter in shear. That is in double shear. Double shear means in two places, top also, bottom also. Okay, and then now we will see. Okay, again this is the socket. See, socket is failing here. This is called across the slot. This is the slot. They say across the slot it is failing. So what will be the area if it should fail? What area should fail? You see, now they will show it. You see, that is the area it should fail. So what is the area? You see, the outer diameter is d1, the inner diameter is d2, and there is a hole also here. Okay, there is a hole for the cutter. So this is t. Okay, what will be the area now? Outside area is pi by 4 d1 square. See, these notations may be differing from uh, from different people. Okay, our notations were different. Okay, don't worry about the notations. Okay, so this outside is d1. Okay, again, now this is tension, this is the socket. Okay, now what they are showing is, suppose in this socket, okay, because of the tensile pull this side, what is happening is, because the cutter is in the middle, so this portion here and the down here, it may fail in shear. See, now they will show. You see, yesterday I was talking about some cake pieces falling. This is like that, you see, those are the areas which should fail. You see here, top also, bottom also, and the back side also. So you should be able to compute the area now. Now this area will be, this is d4 and this is d2. So d4 minus d2 is this dimension, this is c. Okay, d4, see here it is given, d4 minus d2 into c, this will be the area, and 2 it is taken because it is double shear. Okay, now failure of the spigot, let us see. Spigot we have seen yesterday's lecture itself, how spigots are failing. This is spigot. Now it may fail here in shear. See this, like this piece has fallen. Okay, and this actually in our thing this was our d1, but here it is, they have taken it d2, and this is a. So what will be the area if it is d2? It will be, area will be d2 into a and double shear. That means on either side it should fail. Okay, that is 2 times of a into d2. That will be the area. Okay, okay, now failure of the spigot only we are seeing in tension. Again, it may fail, across the slot. Earlier what we saw was the socket failing across the slot. Now the spigot failing across the slot. You see, this is the area that should fail. Okay, the area when we see this is d2 into this is circle is pi by 4 d2 square, and this we have to minus, though it is a little curved we consider it to be a rectangle, and this will be, so area will be what will be the area, pi by 4 d2 square minus d2 into t, that will be the area. Okay, like that. Okay. Okay, now let us see, coming back to our problem, see where we start, where we left yesterday. You see, next point is to find out the thickness of the socket collar. So for this, what we consider is the socket collar is failing in double shear along the two planes containing the two surfaces of the cutter. You see here the cutter is there like this in the side view. Okay, like this is the cutter. Okay, and if you are pulling it, what happens, this piece and this piece may shear off and fall. See, just now in the animation I have showed you. So this is the shaded area will be, this is the this shaded area, this here the shaded area, this is the area of failure. You see, you what is the, see, outside diameter is d2, inside diameter is d1. Okay, so capital D2. So now capital D2 minus D1 will be this one side. Another side is C, and it is failing in two planes. That means here also and here also. Okay. So the total area will be 2 times of capital D2 minus small d1 into C. This will be the area. Now the strength equation will become uh, shear stress, that is tau, is equal to load upon area P by A. This is transverse shear, that's why this area, this formula, load upon area. Okay, if it is a torsional shear we will use torsion equation. Okay, that is different. Okay, so load upon area, load is P, area is this. See, from this equation the thickness of the socket collar C can be obtained. Okay. Okay, but we C can be obtained, but do you know D2? D1 we have no, D2 we don't know. So this step we should not do now. Okay, first in the socket, when we are designing socket, first this step we should do. What? Outside diameter of socket. Outside diameter of socket means this D1. This is what we have to find out. Okay, so you see what we have to do, we have to depending upon the type of axial load, the socket is subjected to direct tensile or compressive stress. Okay, but it is strong in compressive stress, not in tensile stress. Therefore, we are going to design in tension, and there is a tearing across the socket collar. You see, across the socket collar is the weakest spot. That's why we have to design there. See, and across the socket collar, if you see, this will be the cross-sectional area, this shaded area. See, outside is capital D1, inside is small d1. Okay, and then there is a slot for the cutter. Okay, now what is this area? You see, this area is pi by 4 capital D1 square minus pi by 4 small d1 square. Okay, and again they have to minus this also. Okay, this is a rectangle, so rectangle will be capital D1 minus small d1 into t. You see, this is the for area given here, pi by 4 capital bracket capital D1 square minus small d1 square bracket close minus d1 minus d2 into t. This will be the area. You should know how to find out these areas. You see, you should be able to draw the figure for everything wherever possible, wherever you can. You draw the area of figure, and then you write the area of, every time you need not be writing area of tearing, area of shear also. Simply say resisting area capital A is equal to this. Okay, now this will be the strength equation. Sigma T, because it is in tension, is load upon area. This is capital P upon this area. Okay, and from this you can find out D because the others are known. from this strength equation, because we already know T, we know small d1, from this we can find out small d2. Okay, coming to the next step. Next step is diameter of the socket collar. Socket collar, I have shown you in the animation how it is failing. See, socket collar, the area of contact between socket collar and cotter is subjected to crushing stress. Yeah, sorry, this was not there in animation. See, this is failing in crushing. You see, that means what? See here, uh, 1 minute, I will show you the figure. Yeah, this is the figure of our this thing. This is socket collar. You see, because we are pulling this side, this cotter is in the middle, so it will not allow the socket to come away. So this socket collar here and here will be crushing against this, against the cotter. So here and here, these two places crushing is taking place. Okay, that's what we are seeing. So what is the area where it is crushing? This is the thing that is crushing. Okay, this is thickness is T, and here a little and here a little, this shaded portion. So this is capital D2 is the outside diameter, this is small d1. So capital D2 minus small d1 into T, this will be the area. This is the formula for area. In this book, no area separately, sometimes it is not given, but you should give. What I am saying is, three things only. See what type of failure here we are considering. Considering failure of the socket collar in crushing, this should be the heading. Then you should draw the figure and notations, and then you mention what is the area here, and then the strength equation. These things should come. Okay, now because it is crushing stress, so sigma C will be load upon area. Load is P and area is capital D2 minus D1 into T. Okay, so from this what are you finding? T, capital small d1, P will be given in the problem, sigma C also will be given. So only unknown is d2. From here you can find out d2. Okay, after this only you should consider this step. This is the thickness of the socket collar. Socket collar thickness means this is the socket collar thickness, how width should be. I'll show you in the figure here. This is C, this is C. Okay, so if it is being pulled like this, and this piece and this piece falls off, that means it is shearing taking place. So double shear takes place. So this was the in double shear, area will be capital D2 minus small d1 into C, that is here, and double shear because it is in two places. So from this now, because earlier we found out capital D2 also and D1 also, only C is unknown from this equation. Okay, next design of Cotter. Uh, to see Cotter is like this. This already T we have found out only B. You see, you must be wondering, it is tapering like this. So B we are finding. You see, lower distance is less, and lower width is less, and top width is more. So this is the mean width. That means, you can say the center. B, when we are saying, it is the mean width. This is the Cotter. T we have already found out in the before, and only B we have to find out. Okay, now it is failing like this. You see, this is when it is pulled like this much piece is coming, so it is shearing here also and here also. What will be the shearing area will be 2 times of B into T. So that is shearing equation. What are we considering? We are considering the failure of Cotter in double shear. Okay, shear stress induced will be load upon area. Load upon area is 2 into B into T. So T is known, P will be given, tau will be given, only unknown is B. So from this B can be found out. Okay, next coming to the uh, failure of Cotter in bending. In bending, sometimes this like this, some questions are asked separately. Failure of Cotter in bending. You see, when you are asked only for about Spigot and Spigot joint, this part you can omit. But specifically when they ask you, you explain the failure of Cotter in bending, then you have to draw this neat diagram and explain the failure of Cotter in bending. You see, this is the Cotter figure. Okay, you see here, one side, this is the, see, sometimes Cotter Spigot is this side, sometimes Cotter Spigot is that side. So you should understand here we are assuming that Spigot is this side, and no, this is Spigot is this side, and the Spigot rod end will be this side, and socket is this side like this. So this socket, see the socket collar will be, the load will be exercised in a triangular form like this, and on both sides, and whereas Spigot will be exercising by applying load like this in the rectangular form. Okay, so total load that is being pulled is P. See, this Cotter is straight on one side and tapered on one side. Okay, and you see, we are pulling with load P. Okay, load P means, you see, if you consider only half portion of this, that means up to above the line XX, in the center, P by 2 will be applied, and here another P by 2, totally P will be applied. Similarly, when the socket collar is pulling it that side, P by 2 will be applied here. This is a triangular application of force. Okay, and here also another P by 2. So let us consider only one side of the Cotter. Okay, that means only above XX. So you see, we know that this entire distance is what? The entire distance is D1. Okay, and half of the distance is d1 by 2, and this distance where this force is applying out to the x-axis will be d1 by 4. This is the distance, right? Okay, you see, this from here to here is d1, and here to x in is d1 by 2. Okay, and what is this distance? This distance, see, the total is capital D2, and this distance is d1, so d2 minus d1, and see, half of it is d2, and this distance will be 1/3 of it. So this distance that is shown here will be d2 minus d1 by 2 into 1 by 3. That is the distance. Now what we should do, we should take the moments, you see, about the x-axis. You see, one force is making it to, you see, if this force is applying, it is making it to go in clockwise direction, and this is making it to go in the counterclockwise direction. There are two forces. One force is acting at a distance of d1 by 4. Another force is acting at a distance of this plus this. So much distance from the x-axis. Okay, so we have to take the moments. So here moments is given. So that is the bending moment. Bending moment is half of p by 2, this distance, this one, in this now, see, this you see, from where are we getting? From here we are getting, this is 1 by 3 into this, and into d1 by 4. So this is the entire distance. That means, you see, from here to here distance. Okay, that is like uh, again, you see, this person has done a mistake here. This should have been, yeah, can you see now? This is d1 by 2, so this is should be d1 by 2. This is d1 by 2. Why is he using 4 here? It is not 4 here. Okay, anyway, but in the next step he has used 2. Okay, anyway, you remember that this is 2. Okay, because here is d1 by 2. d1 by 2 plus capital D2 minus d1 by 6. This one. This is multiplied by the force P2. This is one moment which is turning it anti-clockwise. And this moment, because of this force, is turning it clockwise. That's why minus P by 2 into d1 by 4. So now P by 2 can be taken common outside, and this will be like this. So bending moment maximum is P by 2 into d2 minus d1 upon 6 plus this can be converted into d1 upon 4. It will become, this is half, this is quarter, so quarter will remain d1 by 4. Okay, so this formula you have to derive and show. That's all. Okay, and then you should say, bending stress is um, bending moment upon section modulus. Bending moment is mx, that is this value that we have found out, and upon z. Z is section modulus. Section modulus is for rectangular cross section. This you should remember from strength of materials. Section. This is TB square upon 6. TB square upon 6. See now, will it be TB square upon 6 or BT square upon 6? It will be TB square upon 6. You see, uh, which of these two values is larger? T is big or B is big? B is big. So the square will be for B. Okay. So like that. So 6 M maximum of TB square, because the 6 has gone up. Okay. So this is the moment, and this is 6 upon TB square. Okay. And then finally you will write the equation like this: bending moment sigma b is equal to P into 2 capital D2 plus D1 by 4 dB square after simplification. So this equation gives the maximum bending stress induced in a cotter. By substituting the value of permissible bending stress in equation 1, the width of the cotter B can be obtained considering the bending failure. It may fail in bending also. See now, cotter, how many ways it is failing? Cotter is failing in shear, cotter is failing in bending, and cotter may fail in crushing also. But that crushing equation we have not seen. Okay. Okay, so earlier also we got B. So the larger of the two values of B can be selected. Okay, finally, the length of the cotter L this is arbitrarily from empirical relation, 4 times of the diameter of the rod. We can take it. Okay. So that is how we have found out. We have designed this joint completely. What are the dimensions we have found out? First, we found out capital D, small d, then D1, then we found out. Okay. Okay, then we found out D2, then we found out T1. Okay, and then we found out this A. Okay, these were the for the spigot, and for the socket we found out what was capital D1, and then we found out capital D2, and we found out this distance C we found out, and for the cotter we found out what was B. Okay, B we found out two ways, one by shearing, another by bending also, whichever is the larger of the two values. Okay, like this the entire design of socket and spigot joint is completed. Okay, so tomorrow we will see another two types of cotter joints. Though they are not so famous, we can see how to design this. See, first you understand how when especially when tensile stresses, compressive stresses are coming, crushing is coming, when shearing is coming, how to find out the area. that is resisting that failure. And you should be able to draw those areas, and from after drawing those areas you should be able to find out what is the equation of that area. Once you know this, you can put in the strength equations, and then you can find out the diameters. Finding out the diameters, or the finding out the dimensions of the joints, this is called machine design mostly. Okay, most part of it is finding the dimensions only. Okay. Okay, today we'll stop here. We'll see some next day. Thank you.